Okay, this is section 5.3, and we're going to start out talking about adding fractions. We know how to add fractions. You just take your two fractions, look at the denominators. The common denominator is the least common multiple of all the factors in the denominator. And so you find the common denominator, you multiply the top and bottom of each fraction by that factor that it needs, and then you combine the numerators and you get one fraction. Well, in this section, we're going to learn how to do that process backwards. It sounds easy, but it actually is quite complicated. But if you understand it, that's the trick. If you try to memorize the steps, you probably will really struggle. So there are lists of steps in the book, and if that makes you feel, if that clears it up more for you, you can look at those. But what we're going to do is really focus on doing some examples and learning what we're actually doing, because really we're just doing this backwards, and it should make sense. This process is called partial fraction decomposition. And the purpose of it is that in calculus particularly, and in other things you have to do in higher math, sometimes you can't do certain things with a fraction that is this complicated. So like this fraction here, you need simpler fractions with denominators that are not such high powers. Partial fraction decomposition is for the purpose, definitely for the purpose of doing what is called integration in calculus, but there are other applications of this also. So we're going to start out by learning how you start the process. If you start with a fraction like this and you want to decompose it, the first thing you do is look at the factors of the denominator, and you write a fraction for every one of those factors. So we have two factors here, x plus 2 and x minus 5. So we're going to write two fractions, one with the denominator x plus 2, one with the denominator x plus 5. And then the numerators will be unknown, but we do know that if we have a linear factor in the denominator, which means x is only to the first power down there, we will put a constant in the numerator, so just a letter like a. And that's true for both of these fractions, that the denominators are linear. So we'll have an a for the numerator here on the first fraction and a b for the numerator on the second fraction. And that's all we would do to start setting it up. This is called the structure or the form of the partial fraction. So the first couple of examples we're going to do, we'll just figure out how to set up the form. We won't actually be doing the decomposition. So we're just doing one step at a time, so we make sure we know how to do that. All right, so we're going to set up the form for the partial fraction decomposition for the given rational expressions. All right, so the first one, it has two linear factors in the denominator. It's already factored for us, so we know we're going to have two fractions. The first one will have denominator 2x plus 3, and the second one will have denominator x minus 2. The numerators will be constants because the denominators are linear. So this will be a and this will be b. So that's all there is to setting up the form for the decomposition. We're not doing the decomposition yet. All right, for part B, on this one, the denominator is not factored yet. So first thing we need to do is factor it. But before that, we will always just check and make sure that the degree of the numerator is less than the degree of the denominator. Because if the degree of the numerator is greater than the degree of the denominator, we're going to want to do long division to simplify the fraction before we decompose whatever's left. But that's not the case here, so we will go ahead and factor the denominator. So numerator, we're not going to factor it. We don't need to. The denominator, we can factor out an x. So we'll have x squared plus 6x plus 9. And we can see that x squared plus 6x plus 9 is a perfect square binomial. So 4x squared plus 10x plus 9 over x times x plus 3 squared. All right, so this time we have three factors here. We have x, we have x plus 3, and we have another x plus 3. So there will be 3 fractions. X, denominator there. This one will have a denominator x plus 3, and this one will actually not just have the factor x plus 3, but it will have the factor x plus 3 quantity squared. So whenever you have a factor that has a power on it, you have to do every power of that factor that is raised to a power. So we have to have x plus 3 to the first power and x plus 3 to the second power. And if this had been x plus 3 to the third power, we'd have to have another fraction with x plus 3 to the third power. So that's not exactly intuitive, but that is what you have to do whenever you have a factor raised to a power. Okay, so the numerator for the first fraction, this is linear in the denominator, so it will be a constant. This is also linear, so it will be a constant. This factor right here is also linear, even though it's raised to the second power. X plus 3 itself is linear, so the numerator will be a constant. So that is all there is to setting that up. Okay, so for part A, let's make sure that the numerator has a lower degree than the denominator, so it's second degree on top, third degree on bottom, that's fine. We need to factor the denominator. That's going to be the first thing we do. So x times x squared plus 4. All right, and the numerator, we're not going to factor it. We don't need to. Okay, so in the denominator, we just have 2 factors. You can't factor x squared plus 4. So we have 2 factors in the denominator, so we'll have 2 fractions. One will have the denominator x, and one will have the denominator x squared plus 4. All right, so x is linear. It's just raised to the first power, so the constant will be in the numerator. X squared plus 4 is not linear. It's not a linear expression. It's a quadratic expression because x has a power of 2 on it. So the numerator has to be 1 degree lower than what the denominator is. It has to be linear on top. So we will write a linear expression, bx plus c. It has to have an x term and a constant term. So when you have a quadratic expression in the denominator, the numerator has to be linear. So bx plus c. B, the degree of the denominator is greater than the degree of the numerator, so we don't need to do any division. We can go ahead and factor the denominator. Actually, the denominator is already factored. You can't factor x squared plus 2x plus 5, so the denominator is already factored into just 2 factors of x squared plus 2x plus 5. So we have to write 2 fractions because we have a factor raised to a power, and so it's just x squared plus 2x plus 5 for the first fraction, and the second fraction has to be the higher power, the next power up for that 2. So these are our 2 fractions that we're going to break this up into, and since these factors on the bottom are quadratic, the numerators need to be linear. So this one will be x plus b, and we can call this one cx plus d. Okay, so when we talk about whether the numerator has to be linear or just a constant, we look at the factor and see what power is on x. If the power is 2, then the numerator has to be a linear expression. And that's true over here as well, even though if you multiplied this out, it would have an x to the 4th. You're not looking at that. You're just looking at the factor that you're raising to a power. So that is a quadratic expression, so the numerator has to be a linear expression. All right, so this one we looked at already, how to set it up. The denominator is already factored, so we're going to have 2 fractions, one with 2x plus 3 and one with x minus 2 for the denominator. And since those are both linear, the numerators will be a and b constants. So if we were going to add these 2 fractions, we would get a common denominator, right? So we would multiply the top and the bottom of the first fraction by x minus 2. So we would have a common denominator of 2x plus 3 times x minus 2. We would multiply the second fraction by 2x plus 3 over 2x plus 3. And that way we would have our common denominator of x minus 2 times 2x plus 3. And we would multiply that out. We would use the distributive property. And the left side looks like it did before. And the right side would end up being a times x minus 2, b times 2x plus 3 over the common denominator. All right, so the denominators on these expressions are now the same, and so the numerators must be the same. So that must equal that. So we'll write that equation. 4x minus 15 has to equal, and I'm using the distributive property to go ahead and multiply that out on the right side. 4x minus 15 must equal ax minus 2a plus 2bx plus 3b. All right, so 4x minus 15, on the right side, I've got 2x terms and I've got 2 constant terms. So I'm going to go ahead and put those together and factor out the x on the x terms. So I'll have x times a plus 2b. So I had an ax and a 2bx on the right. So I factored out the x and I have a plus 2b there. And then I have 2 constant terms, minus 2a plus 3b. So those go together. And then I have minus 2a plus 3b, the constant part of the right side, and that goes with the negative 15. So the x term is 4x. So on the right side, the coefficient of x is a plus 2b. So that must equal 4. So a plus 2b must equal 4. And then the constant part must be negative 15. So negative 2a plus 3b must be negative 15. So now I have 2 equations and 2 unknowns, and I can solve that. I'll multiply the top equation by 2. The a's will cancel, and I'll end up with 7b is equal to negative 7, because when I multiply the top equation by 2, I get 4b, and then I add 3b, I get 7b. And then 8 minus 15 is negative 7, so b is negative 1. And if I plug that back in, I get a minus 2 equals 4, so a is 6. So I found my a and b, and now I can write the partial fraction decomposition for the fraction I started with, 4x minus 15 over 2x plus 3 times x minus 2, and that would be equal to a over 2x plus 3, so 6 over 2x plus 3, plus b over x minus 2, so negative 1 over x minus 2. So that was how I set it up in the beginning, and that is the partial fraction decomposition of that original fraction. And if you were to get a common denominator and add those together, you would get 4x minus 15 over 2x plus 3 times x minus 2. So you can see that it's a little more difficult to go backwards than it is to go forwards. But it's the same process. If you think it through, it makes sense. So let's look at another one. All right, so we're going to find the partial fraction decomposition of this one. And again, we're going to check before we start. To make sure that the degree of the numerator is less than the degree of the denominator, and it is. And then we're going to factor the denominator. So we've got the denominator here. We're going to factor out an x, because that's the only thing we can factor out. So x squared plus 6x plus 9. And so the numerator just is what it is. And so that is going to, we're going to look at what we have. The denominator can be factored further because x squared plus 6x plus 9 can be factored to x plus 3 quantity squared. So I'll just write it again, 4x squared plus 10x plus 9 over x times x plus 3 quantity squared. All right, so this looks just like one of the ones we just did. And we can see that we have 3 factors in the denominator. We have x, and we have x plus 3, and x plus 3 squared. So we're going to write 3 fractions. One will have x in the denominator, one will have x plus 3 in the denominator, and one will have the higher power, x plus 3 squared. We know that x is linear, so that will have a constant for the numerator. X plus 3 is linear, so we'll have a constant in the numerator, but x plus 3 is linear, so we will just have a constant in the numerator. All right, now, what I'm going to do now is, instead of getting a common denominator on the right side and adding all those numerators together, I'm going to do something that is actually easier than doing that. And what that is, it's the same thing, but it's just easier. I'm going to multiply the whole equation through by the common denominator, x times x plus 3 quantity squared, to get rid of all the fractions. So I am multiplying this by the common denominator, x times x plus 3 quantity squared. So instead of getting a common denominator on the right, adding it all up and saying the numerators are equal, I'm just going to get rid of the fractions right away. Okay, so when I do that, I will multiply the first term on the left. It will just all cancel out. That denominator will just go away, and I'll have 4x squared plus 10x plus 9, and that should equal all the stuff on the right. When I multiply by this first fraction, the x will cancel, and I'll just end up with a times x plus 3 quantity squared. When I do the second fraction, multiply it by this, one of the x plus 3's will cancel, and I'll end up with bx times x plus 3. And then when I multiply by this, I'm going to have plus the x plus 3 squared is going to cancel, and I'll end up with just cx. Okay, so now I am going to multiply everything out on the right side. So I will have a times x squared plus 6x plus 9, and then bx squared plus 3bx plus cx. All right, and then I'll go ahead and distribute that a. So I'll have 4x squared plus 10x plus 9 equals ax squared plus 6ax plus 9a plus bx squared plus 3bx, I'm running out of space, plus cx. Okay, now what I'm going to do, I'm going to just go way over here and use up all this space. So I'm going to rewrite this left side, 4x squared plus 10x plus 9. And then on the right side, from this stuff over here, I'm going to put the x squared terms together, the x terms together, and the constants together. So I got ax squared plus bx squared. And then I've got 6ax. And I've got 3bx. And I've got cx. And then I have a constant, 9a. Okay, now for my x squared terms, I'm going to just factor out that x squared. So I'll have a plus b. For my x terms, I'm going to factor out the x. And I'm going to have 6a plus 3b plus c. And then I'm going to have my 9a. So if all of that equals 4x squared plus 10x plus 9, since a plus b is the coefficient of x squared on the right side, it must equal the coefficient of x squared on the left side. So a plus b must be 4. And then since 6a plus 3b plus c is the coefficient of x, it must equal 10. And then the 9 is the constant, so that must equal the constant on the right side, which is 9a. So 9a equals 9. So I have a system of 3 equations and 3 unknowns that I can solve, and once I solve those, I will be able to put those values in for a, b, and c, and I will get my partial fraction decomposition. So I can see that 9a is 9, which means that a is 1. If I plug that into the first equation, I will get 1 plus b is 4. So b equals 3. And if I plug both of those into the second equation, I will get 6 times 1, or 6, plus 3 times b, which is 9, plus c equals 10. So c, 10 minus 15 will give me negative 5. So c is negative 5. So I've got my a, b, and c, and I can plug those in. So the partial fraction decomposition for 4x squared plus 10x plus 9 over x cubed plus 6x squared plus 9x is equal to a over x, so 1 over x plus b over x plus 3, so 3 over x plus 3, plus c over x plus 3 squared, so negative 5 over x plus 3 squared. Okay, here's another one, but this time when I make sure and check if the degree of the numerator is less than the degree of denominator, it's not. So before I try to decompose, I can go ahead and do division. I can do this division and kind of decrease the power of the thing that I have to decompose, the fraction. So I will do that. X cubed plus 4x, I'm going to divide that into x to the 4th plus 3x cubed plus 6x squared plus 9x plus 4. All right, so x cubed into x to the 4th goes x times. So multiply x times x cubed is x to the 4th. 4x times x is 4x squared. So 4x squared goes there. Subtract, you get 0 and you get 2x squared. Bring down your 9x plus 4 and your 3x cubed. All right. Divide again, x cubed into 3x cubed would be 3 times. So 3x cubed, 3 times 4x is 12x. Subtract, these go away, and you have 2x squared minus 3x plus 4. So this is the remainder for this division problem because the power is lower than x cubed. So that's the remainder, so 2x squared minus 3x plus 4 over x cubed plus 4x. Okay, so this stuff right here, that's already as simple as it can be. So when I decompose this thing, I'll decompose it as x plus 3 plus 2x squared minus 3x plus 4 over x cubed plus 4x. So I don't need to decompose the x and the 3 because they're already as simple as they can be. All I need to do now is decompose this fraction. So it's a little bit simpler than decomposing the bigger fraction. So now that the degree of the denominator is greater than the degree of the numerator, I will go ahead and factor the denominator. So I will have 2x squared minus 3x plus 4 in the numerator, and the denominator will be x times x squared plus 4. X squared plus 4 cannot be factored any further, so we are done factoring, and we just want to write our two fractions because we only have two factors here, x and x squared plus 4. So the first fraction will have a denominator of x. The second one will have a denominator of x squared plus 4. X is linear, so I have a constant for the numerator. X squared plus 4 is quadratic. The power on x is 2, so I need a linear numerator. So it will be bx plus c. All right, so now, again, like I did last time, I'm just going to go ahead and multiply this whole thing through by the common denominator, x times x squared plus 4. And that way all those fractions will go away. Okay, if I multiply the right side out, I will have ax squared plus 4a plus bx squared plus cx. All right, now if I arrange this with my x squares together and my x term next and my constant term last, it will look like this, and I can factor out the x squared here. So that'll be a plus b, and then I've got cx plus 4a. So again, I have an x squared term, an x term, and a constant, and that's what I have right here. So the coefficient on x squared is 2, so a plus b must be 2. The coefficient on x is -3, so c must be -3. And the constant is 4, so 4a must be 4. So a must be 1. We already know c is -3. A plus b is 2, so 1 plus b is 2, so b is 1. So I've got my 1, I got my 2, I got my a, I got my b, I got my c, and so now I can go ahead and write this partial fraction decomposition. I've got the x plus 3 that I found by dividing, and the fraction I was left with can be decomposed into a over x, so 1 over x, plus bx plus c over x squared plus 4, so b is 1, so bx, 1x, plus c, which is -3, over x squared plus 4. So this is my decomposition. The denominator is actually already factored. You can't factor x squared plus 2x plus 5. So it's already 2 factors of x squared plus 2x plus 5. So we just have 2 fractions. Both of these denominators have quadratic factors, so raised to the second power on x. So the numerators need to be linear. So ax plus b, so cx plus d. All right, I'm going to do just what I did last time, which is multiply the whole thing through by the common denominator, which is x squared plus 2x plus 5, quantity squared. All right, so I'm going to multiply everything out up here. I've got to use the distributive property. I've got to do the a and the b, so I'll have ax cubed plus 2ax squared plus 5ax, and then I do the b's, so I'll have bx squared plus 2bx plus 5b, and then I've got my cx plus d. All right, now I'm going to arrange my powers of x. So I've got my ax cubed, and then I've got 2ax squared and a bx squared. So I'm going to go ahead and factor out that x squared. So I'll have 2a plus b for that term. And then I'll look at my x terms. I've got a 5ax, a 2bx, and a cx. So if I factor out the x from those 3 things, that's 5a plus 2b plus c. Then I have some constant terms. I have 5b and d, so plus 5b plus d. So I've got an x cubed term. Now on the left side of this equation, there is no x cubed term. There's only x squared, x, and a constant. So a must be 0. 2a plus b is your coefficient on x squared, and the coefficient on x squared over here is 3. So 2a plus b must be 3. The x term has a coefficient of 5a plus 2b plus c, and that should equal 8. So 5a plus 2b plus c must be 8. And then my constant is 5b plus d. So 5b, I don't have room for it. 5b plus d must equal 14. Okay, so I have 4 equations, but really only have 3 because a is 0, and I can start plugging that in to the second equation. So since a is 0, 2a plus b is just b. So b is 3. And then for this equation, if I plug in that 0 for a, I just end up with 2b plus c. So 2b plus c is 8. And then for this equation, I've got 5b plus d. So 5b plus d is equal to 14. All right. Since I already know what b is, I can go ahead and plug that into the second equation. So 6 plus c equals 8, which means that c is 2. 15 plus d equals 14. So d is equal to 1. So I've got my A, I've got my B, I've got my C, and I've got my D. So I can write the partial fraction decomposition for this fraction. And so ax plus b up here, a is 0, so 0 plus b is 3, so 3. And then cx plus d, so c is 2, so that's 2x, plus d is 1, so 1. So I'm going to squeeze this over here, just rewrite the partial fraction decomposition for this fraction. 3x squared plus 8x plus 14 over x squared plus 2x plus 5 quantity squared is equal to 3 over x squared plus 2x plus 5 plus 2x plus 1 over x squared plus 2x plus 5 quantity squared.